Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to handle the topics of probability theory and statistical inference. So you can recall that in the last lecture we had considered the Bernoulli and binomial distributions, and we also understood that in the binomial distribution, if you try to take n equal to 1, that will become the Bernoulli distribution. So now in this lecture I am going to show you that how you can handle binomial distribution or equivalently the Bernoulli distribution in R software. So whenever you are trying to employ these probability mass function or say any probability density function also in R software, there are a couple of objectives that we want to fulfill. The first thing is this: how to generate a random number from that distribution. That means how to generate a number which will look like as if I have conducted this experiment in real life, and suppose if I try to repeat that experiment 100 times, that means if I try to generate here 100 such observations, they will look like as if I have conducted the experiment in real life 100 times. So for that, how to generate an appropriate random number, then how to compute the cumulative density function or cumulative distribution function. Why? Once you can compute the cumulative distribution function, that is CDF, you can compute various types of probabilities very easily, right? And similarly, if you want to compute the probability at any point, that is the value of the density at any point, right, you have to be careful that when we are trying to use the R software, then it will always call it as a density, whereas this concept is valid when we are trying to consider the probability density function. In the case of probability mass function, we call it as a probability mass function, but you don't get confused with those things. So these are some important properties that we always try to find through the R software. So what I am going to do, that I will try to show you all these commands, what are the important parameters, what are their interpretation, how are you going to execute it, how are you going to interpret it. But definitely one request before I move forward: whatever commands I am going to give you here, they are in much detail, but surely discussing all the possibilities, all the options, it is not possible. So whenever you want to understand these things, my very honest suggestion is that look into the help menu of that option. For example, if you want to generate the binomial distribution, try to look into the help menu, and it will give you entire information, complete details, and that will make you complete. My objective here is very simple. Now at this moment you have to ask yourself and tell, do you know anything about that, how to do such computation of binomial distribution in R software? Answer is yes. I am sure that after half an hour when I am completed the lecture, then you will see that okay, what was there, it was a very simple thing, but that is my objective. I want to make you say that okay, that was a pretty simple thing, but it does not mean that it is complete. My job here is to give you confidence that you can learn it. Once you can learn these basic fundamentals, I assume that you are on the track, and then after that you can travel and sky is the limit. So let us begin our lecture and try to see how we can handle the binomial distribution in the R software. Okay, so a discrete random variable x is set to follow a binomial distribution with parameters n and p if its probability mass function is given by probability of x equal to k is equal to n choose k p raised to the power of k into 1 minus p raised to the power of n minus k if k is equal to 0, 1 to n, and this is indicated by x follows a binomial np. This is what we have learned in the last lecture. Now I am coming to the say R software, how are you going to handle it. So, in the R software you can compute the density distribution function, that is CDF, you can compute different types of quantile function, and you can generate the random numbers from the binomial distribution. And here as you have done that, it is indicated by binomial NP. There are two parameters n and p. So, n is going to be indicated by here size, and p is going to be indicated by another parameter, say here PROB prop. And there is one understanding in R that very conveniently we interpret the value of here n as the number of successes, right. How do you define successes? That is up to you, right. Okay. So, now in case if you try to look into the commands, there means I will be discussing here 4 possible commands. Say one here is binom. So, binom, that is the abbreviation for binomial, and D means density. So, the command D binom, and in case if you write down the parameters x, size and prop inside the parenthesis, this will give you the value of the density for a given x, n and here p, right. So, you can compute any type of probability, the value of probability of x equal to k, right. And similarly, if you try to use the command here p binom, p binom, and then this is going to give you the CDF, the distribution function, and inside the parenthesis you have to give a couple of parameters. One here is q, then here is size, which is here n, prop which is here p, and lower dot tail equal to f is a logical variable that can take a value say true or false. So, I will try to show you that how it makes a difference. For example, if you try to see here that in case if you try to take lower dot tail is equal to true, which is actually the default, you compute the probabilities, probability x less than equal to x, which is your here actually fx, or you had written here as a fx. And in case if you make it here false, if it is false, then it is going to compute the probability x greater than x, which is 1 minus f of x, right. So, actually this will be true for all the probability mass functions and probability density function, which we are going to understand in the forthcoming lecture. So, I have explained you here. After this, I will assume that the same story will continue there itself. Okay. So, this is the meaning of this lower tail, and q here is the data vector where you have to give that what is the value of q for which you want to find out the CDF, right. Similarly, this q binom, q binom, this will provide the value of the quantile function. Do you remember we had done the quartiles, deciles, percentiles, etc. They were called in general as quantiles. So, this q binom will provide us the quantile function for a given value of p, and this then you have to specify the size n, probability p, and lower dot tail equal to true. That is the same thing as you have done in the case of p binom, right. And similarly, there is another command here r binom, r binom. This generates the random number. So, this is the number of observation here n. Be careful, this is not the n of binomial NP, but this is the total number of observation that you want to generate, and size here is n, and PROB prop here is p. So, in case if you try to use this r binom, you will get here the random numbers which will appear as if you have conducted the experiment in real life, right. So, this is very useful when you are trying to do different type of simulation experiment. And remember one thing, if this here this size is not an integer, then we get here the outcome NaN, right. What is NaN? Means you have to learn from your R course, right. So, now here are the details of the symbols that I just explained you, right. So, now let me try to take here different types of exercises and try to illustrate you many things, right, in the given time frame. Suppose I want to plot this density of the binomial mass function, binomial probability mass function. Means I just want to know how the observations will look like, means if I try to really conduct this experiment in a real life. So, what I try to do here, that I try to use here the command d binom to produce the probabilities, right. And I try to compute the density at x equal to k, and I try to vary here the k between say 0 to 100. So, k will be going from 0, 1, 2, 3, 4 up to 100. You can take any value, but I am just taking here 100, so that I can show you here clearly. And the value of here n I am taking here to be 100, and suppose I am taking the value of p to be here 0.5, means equiprobable case like as head or tail. My idea is just to give you an illustration that how the different things or different types of information can be retrieved from such commands, which are really going to help you in the data science, right. And after that I try to plot here these probabilities which I have stored in the this function here prob. So, and then I try to plot this this k and here prob like here like this, and yeah, means this main will give the title that binomial probability mass function, etc. Right. If you try to now execute this expression on the R console, you will get here a graph like this one. You can see here at these are the value of here k, this is at 0, the probability is 0, and as the value of k is increasing, right, means probability of x equal to k, that is increasing. You can see here the curve will look like this. It is not actually a curve, these are the individual points, because this is a probability mass function, right. So, you can see here this will look like this. So, you can see here at this moment somewhere, right, this is the average value. You can see here that here n is equal to here 100 and p is equal to here 0.5. So, the mean here is NP, which is here close to 50. So, you can see here at this around this point the values are concentrated equally on the both the sides. And yeah, and if you can see here there is a variation in these values. So, that is going to give you the idea of NP into 1 minus p, which is the variance of x. So, now first let me try to show you this computation on the R console, and then I will move forward. And who can see here that this type of information is really going to help you in real life, because I always felt as a student that what these values are trying to give us and how this probability will look like, how the picture graphics will look like. So, that is what I am trying to do here, and if you try to plot such a curve here, you simply just copy and paste those commands over here. You can see here we are obtaining the same curve that we have obtained here, right. So, yeah, means how to plot and how to use the plot function, now that you have to see yourself, right, because I believe that you have done these things in the R software. So, now let me try to take the example that I considered in the last lecture, in which there was a coin that was tossed 3 times, and the probability of observing the tail was 0.7, it was not 0.5, and the occurrence of tail is indicated by 1 and the occurrence of head is indicated by 0. So, and this x is the random variable indicating the number of tails in each trial. So, there are total 2 cube 8 possible outcomes which are listed here, and the value of x are also given here. And this experiment can be imitated using the concept of binomial distribution. And suppose if you want to compute the probability of x equal to 2, that means any of these 3 events are occurring, then this probability can be computed by just using the binomial distribution probability x equal to 2, which is 8c2 p raised to the power of 2 into 1 minus p raised to the power of n minus x, that is 8 minus 2, and this will come out to be some value here, right. Okay, so now in case if you try to see here the mean value, this will come out to be n into p, and the value of variance, that is NPQ, that can be obtained by here 8 into 0.7 into 0.3, which will come out to be 1.68. But my objective is that I want to conduct the same experiment inside the R console. Yeah, that looks strange, but let me try to show you how you can imitate the same experiment inside the R console, and it will look like as if you yourself have conducted the experiment, right. So, now I use here the parameter size and prob. So, size here is n is equal to 8 and prob here is p, which is given as 0.7, and we know that this the command d binom is going to give us the density, p binom is going to give us the CDF, q binom is going to give us the quantile function, and r binom is going to give us the random numbers that can be generated from this distribution, right. So, now let me try to show you the applications, and I would try to show you that whatever you wanted to compute manually, that can be computed R. So, now if you see, we have computed this value, right. So, now if you want to compute the same value in the R software, now you have to understand which of the command is going to use. This is what? This is density, that means the probability. So, you have to simply say here d binom 2, n is equal to here 8 and p is equal to 0.7, and this will give you this probability which is mentioned here, right. So, you can see here that this computes the density of the binomial distribution with size equal to n and prob equal to p, and you can see here that both the values are going to be the same. And if you try to compute these values on the R console also, you can see here that this you have obtained from the R software, and this you have obtained from the direct computation, right. So, now you can see the probabilities that you were trying to compute manually, they can be computed directly on the R console also. Okay. So, now I try to illustrate the use of P binom. So, this P binom computes the CDF, and CDF was something like here FQ, which is probability that x less than q or less than or x less than or equal to q. So, this q is given here, right. So, now you can have here an option that lower dot tail is equal to true or false depending on your need. Okay. So, for example, suppose we are interested in the same example in probability that x less than or equal to 2, right. So, that means that x takes the value 0, 1 and 2, and this is going to be probability at x equal to 0 plus probability of x equal to 1 plus probability that x equal to 2. So, now this can be obtained by F2. So, now for that I simply have to write down here P binom, then here 2, this 2 is coming from where? Here, and then n and p, and then you will get here the value like this. And the same thing, you if you want to obtain, you can also write down here lower dot tail is equal to true, and you can see here you are getting the same value, because as we discussed, lower dot tail is equal to true is the default, right. If you want to change it, that can be converted into false depending on the need what you have. So, you can see here computation of CDF is very easy, but my question is that what is this computing? That will come only from the theory, that what the CDF of the binomial distribution, and that is why you need a strong theoretical background to understand this data science. And similarly, suppose if you want to know the probability that x greater than or equal to 2, So, that is going to be simply here 1 minus f1. So, now if you want to do this thing, then I have here two options, that I can write down here 1 minus p binom, and with this here 1, this 1 is coming from here, this 1, and NP. So, this will give me here the value of the CDF, or equivalently I can also use here the option lower dot tail is equal to false, and in this case I do not have to subtract like 1 minus f1, but I can simply say here p binom 1 size and prop values and lower dot tail is equal to false. So, this will give me the same value what you have obtained here. So, you can see here whatever way you want to compute that you can compute according to the need of the experiment, right. But definitely if you do not know the value of PDF, CDF, PMF etc., you cannot understand what they are trying to do here. Now, let me try to take here the option Q binom, which is going to compute the different types of quantiles. So, the quantiles are what? They are defined as the smallest value small x, such that f of x is greater than or equal to p, where f is the CDF of x at any given point x, right. For example, suppose you want to determine the 60% quantile. Suppose this quantile here is given by 6, which is described as probability x less than or equal to q is greater than or equal to 0.6. So, this can be directly obtained by using the command q binom. So, and then you have to give here q is equal to 0.6. So, that is coming from here this 60% quantile, right. And then you have to give the value of here n and p, and then you can get here 6. And equivalently, if you want to use here the lower dot tail is equal to true, you can also use it, but you will get the same value here. But now you have to understand one thing, that earlier we had obtained these quantiles using the function quantile, but now here in this case you are obtaining the quantiles from a binomial distribution. That means your random variable is going to follow the probability laws, where the probabilities are going to be controlled by the mathematical form of the binomial distribution. In the other case, you had simply computed the probability without considering any probability distribution, and you can see here that every probability distribution will have a different type of feature. So, these quantiles are going to be changed, and this function helps you in finding out the quantiles from a binomial distribution. And similarly, when we try to consider different probability function, we will have a different commands. Now, we come to the command R binom. So, this R binom is going to generate the small number of random numbers from the binomial distribution with this size and prop parameter which are given here, right. For example, if you want to generate 5 random numbers from a binomial distribution with n equal to 8 and p equal to 0.7, according to your definition, this can be obtained by writing R binom n equal to 5, size equal to 8, prob equal to 0.7, and you can see here that these are the 5 values, and they are resembling as if you have conducted the experiment and got these values, right. And you can see here whatever outcomes I have shown you here, this is the screenshot, right. I will try to show you now these things on the R console, so that you get here more convinced, right. So, let me try to find out here directly from here D binom. So, this is going to give you here the probability for x equal to 2. So, let me try to clear the screen. You can see here this is coming out to be like this, and similarly if you try to compute here this CDF, you can see here this is coming out to be, you simply have to just write this command here like this. You can see this is the same value, and if you try to give here the option of lower dot tail is equal to true, you can see here this is going to give you the same value, right. You can see here this is the same value as here like this. And similarly, if you want to compute here the probability of x greater than or equal to 2, you can just compute it by writing 1 minus p binom. I am just showing you here quickly, so that you can be confident that whatever you are going to get, that is the same thing what I am trying to show you here. So, this is giving you here the 60% quantile, which is here 6, and similarly if you want to generate here the R binom, that is you want to generate the random numbers, definitely now this is not going to be the same when you try to do it yourself, because these random numbers are going to be change every time. You can see if I try to repeat it 3 times, you are getting here 3 sets of random numbers, right. So, here you have to be careful, and now we try to come to one more part. So, this is just for your information, you can just do the same thing, the whatever I had shown you earlier, that I created this curve. Suppose an unfair coin is tossed 100 times instead of 3 times, then definitely if you want to compute the probability at k equal to 0, 1, 2 up to here 100, right, then you can plot here these types of thing, and you can see here this curve will look like this. Since I already have done this job, so I will not show you, but my main part here is interpretation. You can see here this NP here is mean, here is a 100 into 0.7, which is close to here 70, and you can see here this mean value is close to here 70. So, by looking at such curves, you can have a fair idea that in case if k is very low, what is the probability, and if the k is increasing, then how the probability is increasing and after decreasing, right. Okay. And similarly, if you try to do the same thing just by giving here the different type of plot, which was a high density plot, the same thing what you have obtained here, that can be obtained in the height format. Okay, so I think let me show you these things so that you get here more confident. It will just take a couple of minutes. So, if you try to see here, let me try to see here, if you try to plot here, this will give you a curve like this one, and if you try to plot here with type equal to here, say here H, that means high density, you can get here this type of curve, right. So, these types of curve will give you different types of information that we will try to learn in the forthcoming lectures. Okay. So, these are very simple thing, and these are the screenshot of the same thing which I just shown you here, so that you can be confident that I am showing the correct outcome. Okay. So, now let me try to show you that how you can compute a different type of probabilities using the R software. Suppose we consider the same example, and we want to compute here the probability that x is lying between 4 and 6. So, by the rules of CDF, we know that we can write it as probability x less than equal to 6 minus probability of x less than equal to 4, which is equivalent to here f6 minus f4. So, now you know how to compute this f6 and f4 using the p binom command. So, you simply try to give here these values, and you will get here the probability. So, you can see here that whatever you have learned during the CDF, that how to compute different types of probability, they can be computed here directly, right. Now, suppose if you try to take here the example from, say, that you try to generate here R say here random numbers and with the parameter n equal to 8 and p equal to 0.7, and here in this case the theoretical mean will come out to be 5.6 and variance will come out to be 1.68, and now I want to show you that how these things can be viewed from the simulation. So, I try to generate here say the random numbers from the same distribution, and I try to compute their mean and variance. I already had done this thing in the case of discrete uniform, but I want to just repeat it so that I can show you. So, if you try to compute the mean and variance just based on the number of observations, you can see this value is coming out to be 5.4 and variance is 0.933, which are you have to compare with the theoretical mean. And if you try to repeat, you can see that the mean is varying and the variance is also varying a lot. But in case if you try to increase the number of observations, suppose I make it here 1000 observation and then I try to compute the mean and variance, you can see here that these values are coming out to be more closer than with 10 observations, and even the values that you are trying to compute in every repetition, they are also very close. You can see here these are the value of mean and these are the value of here variance. So, I would say that why do not you try to conduct it, you will get a different value. and these are here the screenshot of the same result which I have just shown you. So, you can be confident that at least you will get the same value, at least I am getting the same value what I have reported, and then you can try it yourself. So, now we come to an end to this lecture, and now I have given you in detail that how you can execute this binomial distribution in this R software. So, now this is your turn. Try to take simple example from your assignment books, try to solve them manually and try to solve the same problem using the R software. That will give you more confidence, and then you can understand what type of probabilities is binomial distribution is trying to give you and how are you going to use it. Well, this lecture was in more detail. After that, I am going to repeat the similar things for other types of probability distribution. So, it is very important for you that you will revise and learn this lecture very carefully. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.